types of orbital overlap, sigma and pi bond. You know, covalent bond. What is covalent bond? Covalent bond is formed by mutual sharing of electrons. Now, when this covalent bond is formed, there is a mutual sharing of electrons, means there is overlap of atomic orbitals. So, depending upon the type of overlapping, the covalent bond is divided into sigma and pi bond. Depending on the type of overlap, the covalent bond are separated as, or they are defined as sigma bond or pi bond. Okay, first we will discuss sigma bond. So sigma bond is denoted by letter sigma. So this is called head-on overlapping. Head-on overlapping of atomic orbitals or axial overlap of atomic orbitals. Okay, and because of this head-on overlapping is maximum in sigma bond. Overlapping region is large. So sigma bond is more stable and large amount of energy is released. When sigma bond is formed. So keep in mind that on sigma bond formation, energy released is more, overlapping is more effective, and that's why this bond is more stable. Okay, and overlapping region is quite large. It is written, overlapping region is large. Okay, and at the same time, most of the time S and P orbitals are involved in bonding in most of the cases. Okay, so if we compare these orbitals, so sigma bond is formed between S and S, SS overlapping or EP overlapping or SP overlapping. So these are the three types of sigma bonds formed. In SS, there is one S overlap with another S, and this overlapping is along the internuclear axis. Overlapping is along the internuclear axis, on the internuclear axis. See, what is the internuclear axis? Axis passing through the nuclei of the bonded atoms. This is the axis passing through the nuclei of the bonded atoms, right? Now in PP case, This is p orbital dumbbell shape. So one lobe of each orbital overlap with each other. So this is pp type overlapping. And sp, one s orbital. You know s orbital is spherically symmetrical, and one p orbital. So these are the three types of sigma bonds formed. Okay, out of these, SS is more stable than SP, which in turn more stable than PP. Okay. So in pi bond, there is sidewise or lateral overlapping between atomic orbitals of bonded atoms. If there is sidewise or lateral overlapping, means it is not head on. There is sidewise overlapping. Okay, side to side. Therefore, in this case, overlapping is less. Overlapping region is less than in sigma bond. So bond is comparatively weaker. Bond is comparatively weaker. It is not as strong as sigma bond because here overlapping is less as compared to sigma bond, because in sigma bond overlapping is head on. Okay, but here overlapping is sidewise. That's why bond is comparatively weak. Okay, you can write weak or weaker. Okay, now here only pp overlapping is considered. S orbital can never form pi bond. Keep in mind, S orbital can never form pi bond, and there is only pp overlapping, where, see, this is p orbital, this is second p orbital, they overlap with each other sidewise. This is internuclear axis. So overlapping is above and below the internuclear axis. Means it is perpendicular to internuclear axis. So there are two electron clouds, one above the plane, other below the internuclear axis. If we write it as plus minus, crust and trough, so plus overlap, minus. So it is like this. One electron cloud is above the internuclear axis, other is below the internuclear axis. But overlapping is less as compared to sigma. So let us find out what is the difference between sigma and pi bond. Difference between sigma and pi bond. And keep in mind, pi bond is always formed. Pi bond is always formed between already bonded atoms. Already sigma bonded atom means pi bond cannot be formed alone. Sigma bond can be formed alone, but pi bond is formed when already one sigma bond is there. Okay? So difference between sigma and pi bond. You can write pi like this or pi. Okay. So sigma bond pi bond. Difference between sigma and pi bond. This may be the question of 2 marks. Okay? Many times there is a question. Yes, sigma and pi both are covalent bonds. They are formed by mutual sharing of electrons, but first bond is always sigma bond and next multiple bonds are pi. For example, if we have this bond, these are single bond, double bond, triple bond. So in first case it is always sigma bond. Single bond is always sigma bond. Then here, with few exceptions, there are only 2 exceptions. Sigma bond and 1 pi bond. Here 1 sigma bond and 2 pi bonds. In this case, there is only 1 sigma bond between 2 atoms. Okay, 1 sigma bond. Here 1 sigma bond and 1 pi bond. Here 1 sigma bond and 2 pi bonds. If there are 3 bonds, one is sigma is always 1, other are pi bonds. The bond is formed, sigma bond, the bond is formed by axial overlap of the atomic orbitals. Okay, yes, we have done now that bond, the bond which is formed by axial or head-on overlap of atomic orbitals, that is called sigma bond, and the bond pi bond, the bond is formed by sidewise overlap of the atomic orbitals. Is it visible? Yes. Okay. Second, the overlap is, yes, in sigma bond overlap is large or small? Yes. Tell me. In sigma bond overlap is large or small? Yes. So the overlap is quite large and bond is strong. In this case, overlap is less and bond is comparatively weak, right? S orbital can take part, S orbital can take part in sigma bond formation, but here S orbitals do not take part in pi bond formation, right? Only p orbitals. Okay, s orbital can never participate in pi bond formation. Then the only one lobe of p orbitals, only one lobe of p orbitals they overlap. You saw na? Like this, only one lobe is involved. But in pi bond, both the lobes of p orbital are involved in bond formation. The electron cloud because when atomic orbitals combine, they form molecular orbitals, right? The electron cloud of molecular orbital is symmetrical around the internuclear axis. Okay, here the electron cloud is unsymmetrical. It is above and below the internuclear axis. The bond is formed in the absence of pi bond. Bond can be formed. The bond with sigma bond can be formed in the absence of pi bond. It cannot be can be formed alone. Okay, but pi bond cannot be formed in the absence of sigma bond. Okay. See, free rotation of sigma bond is possible because see, if we have single bond, the single bond, so that can be rotated easily, but if we have double bond, rotation is not possible. Rotation around the internuclear axis is not free. We have to break it to get it free. Okay, so free rotation of the atom around sigma bond is free. Okay, is possible, sorry. But free rotation of atoms around pi bond is not possible. Okay, free rotation of the atom around sigma bond is possible, but around pi bond is not possible because pi bond is along with sigma bond, so that is at least double bond, so free rotation of the atom is not possible. Let us discuss the formation of N2 molecule. on the basis of orbital overlap concept, let us discuss what is the overlapping concept for N2 molecule on the basis of valence bond theory. See, in nitrogen, you know what is its electronic configuration? 1s2, 2s2, 2p, 3. How many electrons are required? First condition, nitrogen, valence shell is involved in overlapping, right? So this is for nitrogen, okay? 2s fully filled and 2p half filled. Now second nitrogen. So when second nitrogen comes closer to it, then these 2p orbitals, they are of opposite spin. They should be of opposite spin. So they overlap with each other. First form sigma bond. This overlapping gives pi bond. Second also gives pi bond. So 2p orbital overlap with 2p to give first sigma bond, and then 2p, next 2p overlap with 2p to give pi bond, and there is lone pair on each nitrogen. So in this way we can explain it. Okay, overlapping concept. So what are the favorable conditions for orbital overlap? Got it? So favorable conditions orbital overlap. Only half-filled atomic orbitals can take part in the overlap. Okay, first condition. Second condition, at the time of overlap, the combining atomic orbitals must have opposite spin. You can see in nitrogen, combining atomic orbitals must have opposite spin, right? Second condition. Now what is the third condition? The overlap must be maximum as far as possible. Overlap must be maximum as far as possible. Okay, so these are the favorable conditions for the formation of bond by overlap or orbital overlap. Okay, let us see the case of F2. So first condition is only half-filled orbitals take part in the overlap. Second condition is at the time of overlap, combining atomic orbitals must have opposite spin. And third condition is overlap must be maximum. Let us take the case of F2. In F2, fluorine has electronic configuration 1s2, 2s2 and 2p5. So fluorine valence shell 2s2 and 2p5. So second F it should be like this. Then okay, so they can overlap and form a sigma bond. And there are 3 lone pairs on each fluorine. Three lone pairs and 1 sigma bond. Let us discuss the formation of H2O. Now in H2O, there are 2 hydrogens and 1 oxygen. So first draw the oxygen. It is 2s2 and 2p4. Like so 2 hydrogens. So one hydrogen right this side, other hydrogen you can write on other side or on the same side you can write anywhere. Now this hydrogen has up spin, oxygen has up spin, so hydrogen should have down spin in order to overlap. This hydrogen has oxygen has up spin, so hydrogen should have down spin to overlap. So 2 sigma bonds are formed and it has 2 lone pairs. So oxygen, 2 sigma bonds and 2 lone pairs. In same way you can draw for ammonia. So in ammonia we have nitrogen, so nitrogen there is two s2 2p3, so 3 hydrogens, so up spin it should have down spin, up spin it should have down spin, up spin it should have down spin. So 3 sigma bonds are formed. So here there is 1 lone pair and 3 sigma bonds. Okay, so why these atoms combine with each other? To become more stable. That means bond is formed when they become stable. So what about helium? Helium cannot form bond. Why is it so? Helium is already stable. When there are 2 hydrogen atoms come close to each other, attractive forces are more than repulsive forces. And when 2 helium atoms come close to each other, repulsive forces are more than attractive forces. So that is the concept of valence bond theory. That's all we have done this overlap concept. So let us take two hydrogen atoms, HA and HB. Now in hydrogen there is nuclei and one electron each. There are nuclei and one electron each. So hydrogen A has nucleus A and electron. So this nucleus attracts its electron. Second nucleus also attracts its electron. This nucleus of first hydrogen, A hydrogen atom, nucleus of A attract electron of A and nucleus of B attract electron of B. When they are isolated, they are separated. One. Now when they come close to each other, what happened? They continue to attract each other, but now this nucleus repel nucleus of other atom. This electron repel electron of the other atom. These are the new repulsive forces. See, these are the repulsive forces. Means force of repulsion. Nucleus of A repel nucleus of B. Electron of A repel electron of B. Okay. So these are the repulsive forces. Now come to attractive forces. We have already seen that nucleus of A attract electron of A and nucleus of B attract electron of B. But now when they come closer, say nucleus of A is attracting nucleus of electron of A, nucleus of B attracting electron of B. These are the old forces. Now electron of B attract nucleus of A. New attractive force. Nucleus of A attract electron of B and nucleus of B attract electron of A. Okay, these are the forces of attraction and these two are forces of repulsion. But attractive forces are more than repulsive forces. That's why when they come closer, as attractions are more, then energy is released, continue to release, and it reaches minima and then increases. So this is the minimum, and this is called bond length. I think we have done this part. Here force of attractions are greater than force of repulsion. Force of attraction is equal to force of repulsion. Force of attraction is less than force of repulsion. I think we have done this. This is called valence bond theory. And this equilibrium distance between the two atoms when potential energy is minimum, that is called bond length. Okay, helium-2 does not exist. If question is why is helium-2 does not exist on the basis of valence bond theory, then we can explain it like this. In this case, we can say that attractions are more than repulsions. Why helium-2 does not exist? Why helium-2 does not exist? If question is this, then nucleus of A in helium, let us consider two atoms. Nucleus of A, first electron, second electron. Nucleus of electron of A1, A2. First electron of A, second electron of A. First electron of B, second electron of B. Okay. So this nucleus has two electrons. Second nucleus also has two electrons. Okay. So if we talk about attractive forces, nucleus of A1, nucleus of A with A2, they are already existing. Nucleus of B attract nucleus as an electron of B, but when they come closer, then nucleus of B also attract electron of A. Nucleus of B also attract electron of A. Okay. Nucleus of A also attract this. That means nucleus of A is in attraction with EB1 and nucleus of A is in attraction with EB2. So these are the attractive forces, right? Because each electron attract both the nuclei. Each electron attract both the nuclei. Total 4 electrons, so 8. 1, 2, 3, 4, 5, 6, 7, 8. Now come to repulsive attractions. Nucleus of A, nucleus of B. EA1, EB1, EB, EA2, EB2. So nucleus of A repel nucleus of B, electron A repel electron B, electron EA2 repel this, EB1, EA2, EA2, EB2. Even EA1 repel EA2, EB1 repel EB2. So repulsive forces. These are the attractive forces. So we write repulsive. Nucleus of A repel nucleus of B. EA1 repel EA2. EA1 repel EB1. EA1 repel EB2. See, one electron repel 3 other electrons. So there are total 4, so total 12. So these are the repulsive forces, and repulsive forces are dominating over attractive forces. Always. That's why helium atoms will not come close to each other to form a bond. Means if we write the diagram, means potential energy diagram, it should be like this for helium-2. It is always upward. It will never down. So there is no minima in the potential energy diagram. Okay, that's why helium-2 does not exist. So this is all about valence bond theory.